Applications of exponential functions are some of the most interesting and diverse applications that we'll see. They can span from population growth or decay, for example, or business applications with interest, or carbon dating, or radioactive decay, and so on and so forth. And today we will study one of the more basic exponential model. The idea is if you have growth or decay, you have the amount, whether it's money or population and so on, equals to A0, which we'll call the initial amount, times E. This is the E, the exponent or the base that we came across in previous sections, 2.718 and so on. It keeps on going to the power of KT. And if K is positive or negative, it determines if we have growth or decay in our hands. And T is the time. Sometimes it's in years, sometimes it could be different. And A of T is the amount at time T. Okay, so one of the applications we're going to talk about in business is present value. We have studied compounding interest equation before, but what if we instead of knowing how much we're going to put in the bank and trying to figure out how much we're going to have sometime in the future, what if we're trying to save, let's say, for a car or for college education for our children and so on? How much should we deposit right now? Okay, so it's called a present value. And you can either plug in A and try to solve for P, or a little bit easier if you do it right away. So notice if you divide both sides by this portion, 1 plus r over n to the nt power. So instead of the division, note how we can write it with a negative exponent here. And now we can have the equation for present value or principal. It's really the same idea. So let's take a look how we can use this in a problem. So a company must pay a $307,000 settlement in 3 years. What amount must be deposited at 6% compounded semi-annually to have enough money for the settlement? So this is a good question. How much should they deposit now? Well, notice how I set up the equation. We know the future amount is $307,000 times the rate is 0.06 divided by 2. Semi-annually means twice per year. To the negative, notice I used a little negative on your calculator, otherwise you'll get an error. You can put in -6 if you'd like, instead of doing 2 times 3. But here's what I did, and I found that they must deposit $257,107.67. So notice they don't get a whole lot of money by depositing. They have to still have, because in 3 years you still have to have fairly the amount that's fairly close to what you're trying to achieve. But still, they earn a fairly decent amount of interest of $49,000 and almost close to $50,000 actually. So you can find interest the same way. So now here's a question. Suppose the company can deposit only $200,000 now. How much more will be needed in 3 years? So this is going back to the situation if we know the initial amount. How much would they have in 3 years? So I calculated this with the compounding interest equation. Notice it's a positive power or exponent. And I got 238,000 around there. And how much should they put in? So the remaining amount, I basically subtracted it from how much they will actually need to have. And so they will still need to come up with 68,000 or around $70,000 in about 3 years. And suppose the company can deposit $200,000 now in an account that pays interest continuously. I haven't seen this in banks recently, but it's interesting that it still exists or can happen. What interest rate would they need to accumulate this exact amount in 3 years? So I used the continuous compounding interest and I plugged in the P. I used basically the same kind of idea. So we don't know what the rate is. So I plugged in 307,000 equals to 200,000 e to the r times 3. So how would we solve it? Well, here's where we can use logarithms. But let's divide by the initial amount. Actually, not divide by 3 yet. You're supposed to divide by 200,000. Let me fix this real quick. So I fixed this minor typo. We're supposed to divide by 200,000 first. So what I got was 1.535 equals to e to the r times 3. So then we're going to have the exponential. And how do we solve it? Well, we can take a ln of both sides. And recall that ln and e actually cancel each other. So what are we going to have? Ln of 1.535 equals to simply r times 3. Notice how ln and the e cancel each other. Not literally, but they do cancel. Again, never try to literally cancel them because they're not equations. It's a function. But you still end up with just the exponent. And then how do we solve it? Well, we divide by 3. This is where we divide by 3. So it would be ln of 1.535 divided by 3 equals to this decimal, 0.1428, or about 14.28%. So that's a high interest rate. Even if it's continuous compounding interest, I mentioned it doesn't mean that you're going to earn a lot. So it's a very high interest rate, which I think is a little unreasonable. So they need a little bit more than $200,000 to deposit in order to come up with the money in 3 years. Here's another situation. What if we know the sales of a new model of compact disc players? Well, that's going way back in time, I suppose. So here is S of x equals to 1000 minus 800 e to the negative x power, where S of x is the number of sales in how many units, and x is the number of years of the disc player has been on the market. So find the sales in year 0, or the initial amount, I suppose. So if I put in 0, I put in negative 0, but it's the same as 0. E to the 0 is 1. So notice it's the same thing as 1000 minus 800. So we're going to end up with 200 units. And that's the answer. And here is the opposite situation. In how many years will the sales reach 500 units? What if we know the sales and we're trying to find the time? So notice I plugged in 500 equals to 1000 minus 800 e to the negative x. Again, let's subtract 1000 first. We're trying to isolate the exponential portion. So I end up with negative 500. On the other side, we divide by negative 800. So notice I get 0.625 equals to e to the negative x. Let's take a ln of both sides. What would we get? A ln of 0.625 equals to negative x. And so if we divide that by negative 1, we get 0.47, or about 0.5 years, so about half of a year, or 6 months. Will the sales ever reach 1,000? Well, this is a good question, but the answer is no, because this exponential portion right here, it may get very close to 0, especially the more years pass, but it will never actually reach 0. It will always be a slightly positive number. And so no, 1,000 is like upper limit, essentially, that can never reach. Is there a limit on sales for this product? If so, what is it? Well, I just mentioned the word limit. The answer is yes, and it's 1,000 units. And that's it for this section. No, actually, here's one more. Radioactive decay. So let's do one interesting application. Find the half-life, if you remember biology courses, or if you haven't taken it. It's essentially it's time when half of the radioactive substance remains. So here we're given this equation, and this is plutonium-241, a radioactive substance. We don't know the initial amount, but that's okay. We can still solve the problem. I basically set this up as 1/2 A0 equals to A0 e to the this exponent right here. Since we divide both sides by A0, well, we can cancel. Here is where we can cancel them. Let me show you. And so we end up with 1/2 equals to e to the negative 0.053t. Again, we can take a ln of both sides. And we end up with a ln of 1/2 equals to the exponent only. So you can solve for t as a ln of 1/2, make sure close parentheses, divided by negative 0.053. So we end up with 13 years approximately. And now that's it.